Okay, in this next section, 11.4, what we are now interested in is looking at, with the help of the Maxwell relationships, developing some thermodynamic relationships to allow us to determine the changes of entropy, internal energy, and enthalpy from obtained measured property data. So before we said that we may have easily measured temperature, pressure, volume, as well as C sub P as a function of temperature. And with that, then we are interested in utilizing those Maxwell relationships in order to determine how other properties change. And so the first thing we'll look at is the concept of a phase change. What happens for a pure substance when it goes through a change of phase, for instance, from solid to liquid or from liquid to vapor. The Clapeyron equation is an equation that represents the change in the enthalpy during one of those phase changes. And again, the phase change could be vaporization, which is from liquid to vapor, sublimation, which is solid to vapor, or melting, which is solid to liquid. And so this equation can determine the change in the enthalpy during that process during a constant temperature process, because we typically think of the phase change occurring at a constant temperature. And we can then use this equation and evaluate from pressure, specific volume, temperature data the resultant change in that enthalpy process. And so what we can say is that at a fixed temperature, which would also be at a constant temperature, we know that the change in enthalpy is simply equal to dTdS. And again, because of the fact that we have at a constant pressure, when we looked at one of those equations we had before, there was a second term associated with this, but that second term was with respect to delta P or dP. And so when we have a constant temperature, constant pressure process, that term went away, and we then have simply the enthalpy change is directly related to the change in entropy. And so with this in mind, as we go through the phase change, for instance, from liquid to vapor, we could integrate both sides of this equation. And since temperature is constant, it can come out of the integration, and we then can relate the delta H to equal to the H at the saturated vapor condition minus H at the saturated liquid condition. That's the enthalpy change across the dome, and we can relate that then to the entropy change across the dome. And so the Clapeyron equation gives us this representation of enthalpy and entropy. We know that enthalpy is directly related to the internal energy and the pressure specific volume, and so we can write another equation, and that is that the change in the internal energy across the phase change can be related to that change in the enthalpy across the phase change. And then we have the term which is pressure times the change in the specific volume. Okay, now that we have that relationship for what is occurring across the phase change, the next step is developing what is referred to as the Clapeyron equation. And the Clapeyron equation looks at that phase change process, and it uses one of the Maxwell relationships that was originally discussed. And if I back up and show you this particular Maxwell relations, and so during the phase change process, what we know is that that pressure and temperature are not independent of each other. And so this particular partial derivative with respect to specific volume becomes the total or the change of pressure with respect to temperature during the saturation process. And so this particular term here is related to the saturation pressure temperature relationship. And we see that that's equal to the partial of entropy with respect to volume during a constant pressure process, which we know the phase change is. And so with that in mind, we then can say that what we had before is this term right here, this change in enthalpy over temperature, change in entropy over temperature was related to the change in the entropy. The enthalpy over temperature was the change in the enthalpy. And so what this equation then, this part right here is the change in the entropy divided by the change in the specific volume. And so this term comes from the partial of entropy with respect to volume. And so it becomes this term here. And so we see that this term is the left-hand side, and this term here is equal to the right-hand side. And so the Clapeyron equation then can be written in that form right there. And so this is valid for any phase change that is occurring at a constant temperature, constant pressure, whether it's in this case a boiling process, a condensation process, a sublimation process, a melting process, any phase change. And so we can say for that particular phase change, if we designate the one side as being double prime and the other side being prime, we can write it in a generic form like that. Now, if we now take this equation and look at lower pressure conditions wherein we have the possibility of the ideal gas behavior, what we know about ideal gases is that the specific volume, prior to that ideal gas becoming an ideal gas, the specific volume change as the substance goes from liquid to vapor, we know that V sub F is much, much smaller than V sub G. And so this term right here can then be replaced with just V sub G because the V sub F is small. Now, we also know that the log or the differential of the logs of pressure is just simply 1 over P times the differential of pressure. And so if we put a 1 over P into this equation here and a 1 over P in this equation here, we then know because the fact that 1 over P times this V, since that is PV times T, and we know for an ideal gas that PV is equal to RT. And so by setting this up as the change in the natural log of pressure, by adding the extra delta 1 over P, we then can write that as the numerator, and now this term here becomes RT, which is the PV for an ideal gas, times another T. And so the Clausius-Clapeyron equation for a phase change going between the liquid condition to the vapor condition then can be written in this particular fashion for an ideal gas. Now, in the text, there was an example problem where they wanted you to take a look at some of the data in the back of the book and evaluate this term. And so again, all that this really is the change in pressure with respect to temperature during the saturation process. And so this information is given in the saturation tables as just the first two lines, the pressure temperature line. And so for every pressure, there is a saturation temperature. For every temperature, there is a saturation pressure. And so if we were to plot this, we would see pressure as a function of temperature. We would have a curve, and that curve would correspond to points taken right off of pressure, volume, temperature property data for water going through a phase change. And so if we had that data from our chart or possibly from the test software, this left-hand side then, if we evaluate it at 100 Celsius, is really just the slope of that line at that 100 Celsius. There's a temperature and a pressure associated with that, and the slope there is equal to the left-hand side, how the pressure changes with temperature. And then we can use the data from the table to see if indeed that slope that we calculate is related to the change in the enthalpy across that phase diagram. And that is HFG in most of our tables, divided by temperature. Now temperature would have to be in absolute units, and then divided by the volume change across the phase change. And so one could take a look at the data and see if indeed the Clapeyron equation holds for phase change for whatever substance you have a saturation table for. And that's what this particular example is asking you to do. Okay, now having looked at the phase change type of regions, let's take a look a little further at some of the single phase regions. So if we are right of the dome, we're in the superheated region, let's say, of a substance, of a pure substance. That is a single phase region. And let's say that we were interested in determining the relationships or determining values of entropy, internal energy, and enthalpy in that particular region. What we do know already in that region is the pressure, volume, temperature information from experimental data, as well as C sub P and C sub V as a function of temperature. And so what proceeds here then is more detailed in the textbook, but if we assume that T and V or T and P can be used to define a state, okay, those are the two independent properties, we can go back to the original portion of this chapter and say, well, let's assume that we can write an expression for entropy as an exact differential with respect to temperature and pressure. And we can also say, let's assume that enthalpy can be written as an exact differential in terms of temperature and pressure. And from those two exact differentials then, we can show through the use of Maxwell's relations and the definition of what an exact differential is with respect to all the partials and everything, we can show that the change in entropy in a single phase region can simply be related to two integrals, one integral integrating from state 1 to state 2 along due to changes in temperature, and another integral integrating with respect to a change in pressure. And the same thing, if we're interested in establishing the value of enthalpy, at some points, at points in that single phase region, it can be shown that similar expressions can be obtained. Now, what you'll notice here on the right-hand side is that all of those integrations are a function of information that we already know, that we've experimentally obtained. And so what we're attempting to do is to use that information and establish maybe a reference point. Let's say S1 and H1 are some reference point in the single phase region. What would be the entropy or the enthalpy at any other place in that single phase region relative to that reference point? And so this is how one would establish that with these set of equations. And so, for instance, now if we want to go from state 1 to state 2, okay, now I jumped ahead here. I think that, when I jumped ahead here, there's actually two equations here in this first set, this first slide. We make the assumption that entropy and internal energy are functions of temperature and volume. And again, the textbook shows how we can establish these two equations. Likewise, if we assume that temperature and pressure are our two independent properties, we can then write an expression for the change in entropy and the change in enthalpy as a function of what's happening to the temperature, pressure, volume, and specific heats. And so if we now look at that first slide, and let's take a look at this equation. So what this equation is asking us to calculate is if we have a reference point in the single phase region, let's call it state 1, and we want to determine what the enthalpy is at another point. And if these 2 points happen to be on constant temperature lines, okay, so we know that on a pressure volume diagram, a constant temperature line comes down, goes across, and then goes into the superheated region. And so if this point 1 is at temperature 1, a constant temperature line, and this point here is at temperature 2, at the temperature 2 line, what we can do is we can perform the movement from 1 to 2 by first of all integrating along a constant temperature line, temperature 1. Now when we say integrating across a constant temperature line, this term is equal to 0. So as we're going from 1 to point X, this term is equal to 0, and this term right here we could evaluate. And so we go from 1 to X by evaluating this term here. Once we now get to X and we want to go up to Y, Y is at the same volume, then along this particular path, this term, the second term is 0 because dV is 0, but what we may have then is we may know the C sub V is a function of temperature at a constant volume. And so this is experimental data. And so from X to Y, we evaluate it in this fashion here. We take the integral of CV dt and we obtain the change from X to Y. And then once we get to Y, we then can go up a new constant temperature line up to this new point 2. So from Y to 2, again, this term would not contribute because the temperature is not changing, but this term right here then, where we then can evaluate this particular relationship as we change the value of V. So we're integrating from here to here through the V variables and knowing the information here. Again, we would be able to obtain all of these terms from our experimental data. And so by doing that, we then can map all of the internal energies in the single phase region. Again, all are referenced to some point that we may want to establish as a 0 point. And so this same process in the textbook, this same process is done for the other changes. And again, it's basically utilizing information along constant temperature lines and constant volume processes. Okay, in this next section, there are some other thermodynamic relationships that make sense to know. And as we can see here, there are four of them shown here. One is referred to as the volume expansivity, and it's designated as beta. And what the volume expansivity is the change in volume of a substance with respect to temperature at constant pressure. So if you have a constant pressure process, this is how much the volume changes as temperature changes. And so it's expanding or it's contracting. And so that is the value here. Now, this parameter is actually not really the change in volume, but another volume is added here, 1 over V. And what this does is it non-dimensionalizes the volume. And so 1 over V dV is really the change in the log of V. And what that does is that gets rid of the volume associated with this particular parameter. So the units on this volume expansivity then is a fractional change, because that's all that V over V is. dV over V is just a percentage or a fractional change, and then this temperature is per degree. And so the units on the expansivity is fractional change or percentage change per degree of temperature change. We can do the same thing for the isothermal compressibility. It is now the change in the volume, and again, it's the relative change in the volume per change in pressure as we allow temperature to remain constant. So it's the isothermal during a constant temperature process. How much does the volume change as we change the pressure? And so an isothermal compressibility would be, as we squeeze down the substance, how much is that, what fractional amount is that particular substance changing with respect to volume? Another isentropic compressibility, alpha, is done in the same fashion. It's a fractional change in the volume per change in the pressure, but with entropy being constant. So if we were able to do that in an isentropic fashion, we then would see that that's the isentropic compressibility. Again, the units on that would be a fractional change per pressure unit, just like this one up here was a fractional change per pressure unit. And then finally, our last term here is the speed of sound. And I already introduced this speed of sound to you earlier in terms of how does the pressure change with respect to the density changing. We did this before for one of our problems. We basically handled it by looking at an incremental change in pressure for an incremental change in density. And during an isentropic process. But if we are, instead of density, if we are thinking about having a gas, which we usually represent with respect to specific volume, which is the inverse of the density, it takes on this form here. And the units on this, if you go through the units, you would see that the units of this would actually come out as meters per second. Again, watching for the pressure units and the specific volume units and adding a factor of 1,000 if necessary in order to get it into meters squared per second squared, that then gets taken by the square root. Some of the other relationships involving specific heats, the C sub P and C sub V, it turns out that the difference between those two parameters happens to be related to some of the changes of the pressure, volume, and temperatures given in this particular fashion here. We can write this same equation in terms of the kappa and the beta that was just previously defined, and so you could go back and check that out. We know that the ratio of specific heats, or K, is C sub P over C sub V, and again, those can be related to changes in the various thermodynamic properties, and that K can be shown from the previous parameters to be related to kappa over alpha. We also, since the speed of sound was equal to this, bringing in the ratio of specific heats, we see then for an ideal gas, this is when we have an ideal gas, we can do that. We then find that for an ideal gas, C is equal to the square root of K, the ratio of specific heats, times RT. And so that shows us the half power dependency of the speed of sound with respect to temperature. It also shows that the ratio of specific heats has an effect on the speed of sound. If we have if we have air which has a K equal to 1.4, we see that it has a certain speed of sound. And if we have a very large molecule that may have a C sub P over C sub V, or a K close to 1, we see it has a reduced value of the speed of sound. One last parameter that I want to discuss is what is referred to as the Joule-Thomson coefficient. And the Joule-Thomson coefficient is given by this mu sub J. And it is, for a substance, it is the partial of the temperature with respect to pressure during an isenthalpic process. And so it is how the temperature is changing as the pressure changes. Again, during an isothermal process, isenthalpic process. And it turns out that this gradient, this term here, can actually be shown to be related to the C sub P and some of the other terms. So let's take a look at that Joule-Thomson coefficient, and let's think about how could we, or where have we seen isenthalpic process. So the question is, where have we seen constant enthalpy types of processes? And we have seen constant enthalpy processes in our expansion valves. And so what you see here on the right-hand side is an example of something that would be an expansion valve. Basically an inlet at a temperature and a pressure, a substance would be coming in, and it would go through a porous plug and then a valve. And so what happens is the presence of this valve then causes the pressure to drop. Okay, and so the question is, when that pressure drops, if we make the assumption that this is isenthalpic because there's no work or heat transfer occurring, the question is what happens to the temperature when the pressure drops? And so that Joule-Thomson coefficient will tell us what happens. And so if I were to take a substance, a pure substance, and plot temperature versus pressure, we recognize that on such a curve, such a plot, we have a line that corresponds to the dome. And the dome exists between the critical point and the triple point, where we have liquid and vapor. We also have at the triple point, we have liquid-solid interface also. And so basically this is the dome. And what we can also then plot are these lines here associated with, the various processes that are occurring as we change the pressure. And so if we come in at a given temperature and pressure, we may be at some point here. And so as we then change the pressure, what happens to the temperature? And so on here, these are lines of constant enthalpy. And so this is then telling us what happens as the pressure goes down. And so for this line right here, obviously as the pressure drops, the temperature drops, and so on. And so, however, there are some situations where as the pressure drops, I think I misspoke there, as we see in this particular case, as the pressure goes up, the temperature goes down. If we want to think of it the other way, if we're at a pressure and we're lowering the pressure, okay, if we're lowering the pressure and the temperature goes up, we have that effect. Okay, there is, for some gases, there is a point that as you lower the pressure, you see the temperature drop. And so anything on the left side of the in what is called the inversion state corresponds to a substance whose temperature drops as the pressure is dropping. Okay, and so we have seen that for these constant enthalpy lines that cross over into through the dome. Okay, so when we have some of those, what we see is we see that we have that decrease in the temperature. So what we have seen for our refrigerants very significantly is that as we come in the saturated liquid condition at a high temperature, high pressure, and we go through the expansion valve to a lower pressure, we see the substance flash into the dome and to a much lower temperature. And those would correspond to the curves down here. Again, the slope corresponds to the change in temperature with respect to pressure at constant enthalpy. And so the slope corresponds to the magnitude of the Joule-Thomson coefficient. And so the Joule-Thomson coefficient is going to be, the magnitude of that is going to be how much the temperature changes with pressure, and whether it's positive or negative tells us what happens to the temperature as we lower the pressure. And so what we're looking for in a refrigerant would be a substance that has a positive Joule-Thomson coefficient such that the temperature drops as the pressure drops in the isenthalpic process. And so anything this way from the inversion state is a positive Joule-Thomson coefficient. Anything over on this side is a negative Joule-Thomson coefficient, wherein as you lowered the pressure, the temperature actually would go up. Okay, so with that in mind, we're going to stop at this particular point, and we're going to pick up next time on the compressibility charts, or the generalized charts for enthalpy and entropy based on the compressibility charts.